So now we're moving on to double replacement, and it's very similar to single replacement, but now you have two compounds switching with each other. One thing you probably want to write down is does not depend on the activity series. Remember, that's only for the single replacements. But what's happening here is you have ions of two compounds. So you have two compounds reacting. And this is really important. So either underline it, bold it, something. But it's taking place in an aqueous solution. And if you remember, you should, but if you remember, an aqueous solution means that it's in water. It's dissolved in water. And this is important because it gives the chemicals freedom. If you're solid, you're very trapped and you're not able to really move around easily. But if you're in aqueous solution, the ions can flow and move and actually interact with each other much easier. So typically what happens is you have your double replacement and it's in aqueous solution, and what happens is you make one of three things. You either make a precipitate, which you definitely want to know, an insoluble gas, or a lot of times you'll make water or some kind of molecular compound, which means a covalent compound. So you definitely want to know that double replacement takes place in aqueous solutions, and you definitely want to know the three things that they can form. There is a section on this in your book that you need to read. It's about net ionics. So you can write that down. Read section on net ionic in book. It's a brief introduction, and we're not going to spend that much time on it, but it is something you should know how to do and understand. Like basically what a net ionic is you're getting down to only the really important chemicals. Here's the general equation. Your two metals typically switch. So A was hanging out with X. And back here he switched. Now he's hanging out with Y. And B was hanging out with Y. And now he's hanging out with X. One thing that is tricky with double replacements that you have to make sure you're doing is you need to make sure that the metals switch places. So a metal always has to be bonded to a non-metal. Sometimes people start mistaking them and they put both metals together and both non-metals together. So just be careful when you're doing these. We have a slide where we're just going to look at some examples, and then we're going to do a couple, and that'll be it for double replacement. So here's an example. We have an example of each kind. We have a precipitate, gas, and everything. So we have our precipitate first. And what you can see here is the potassium and the lead are switching. So potassium was with iodide. What he does is he goes to the back, and he's hanging out with nitrate. And then lead is jumping up front. He leaves nitrate, he goes up front, and he's hanging out with lead iodide. And if you're forming a precipitate, you can actually figure out what the precipitate is by looking at a solubility chart. And that's actually covered in your book as well, so you should read that. You can actually tell which of these would be the solid and which of these wouldn't be. If we look at the next one, we're making a gas. And again, the metals are just switching. Well, the positive ions are switching, I should say. So iron was with sulfur. Now he's hanging out with chlorine. And hydrogen was with chlorine. And now he is coming up front and he's hanging out front with hydrogen. Now, a couple of things people ask me. One thing is they say, like, does it matter if I put iron chloride in front of hydrogen sulfide? No. The order of the actual compounds doesn't matter. Like, it doesn't matter if you have FeCl2 first or second. However, what does matter is if within the compound, you need to make sure that Fe is before Cl. The positive thing always becomes before the negative. Like when you're telling your parents bad news and you're trying to tell them something good first, the positive guy always comes first. And this right here is a gas. You wouldn't necessarily know it was a gas, but this is actually the gas that's responsible for the smell of rotten eggs. So isn't that wonderful? And last one down here is another double replacement here. We have hydrogen and sodium switching places. Hydrogen goes out back and he hangs out with hydroxide. So what this would look like when you wrote it is HOH. And, I mean, you're welcome to leave it that way, but it makes sense that if it's HOH, you could just write it as H2O, and that is a liquid. So, biggest things with double replacement, you're not doing the activity series. You basically as long as I'm showing you the double replacement, you can just write them. You can assume that they occur. You don't have to worry about does it occur or not. And you want to know that it's going to make one of three things: a precipitate, a gas, or a molecular compound / water. And our last ones, we're going to do a couple. So we have right here, we have sodium chloride and magnesium sulfate, and they are going to switch partners. So what's going to happen is we are going to I'm going to bring magnesium up front. So I have MgCl, and I'll come back to that in a second. That means sodium is going to the back, so I make NaSO4. So I kind of just figure out who's together first, then I go back and balance my charges. Magnesium is +2, chlorine is -1, so that means I'm going to need 2 chlorines, so I put a little 2 there. For my second guy here, sodium is +1, sulfate is -2, so I'm going to need 2 sodiums. And then the very last thing you do is you say, okay, do I need to actually balance anything out front or anything with like coefficients? And it turns out I need 2 salts. Second one, we have calcium chloride and silicon dioxide. So again, I'm just making little notes so I remember who's going where. I'm going to bring silicon up front. He's going to hang out with chlorine. And that means calcium is coming out back with oxygen. Now, one thing you have to be careful of is silicon can have a lot of charges. He has Roman numerals. So you have to figure out what Roman numeral he is. And this is actually a little tricky. If we think of our oxygen, let me just move this so you can actually see it. We know that oxygen is -2, and there's 2 of him. So we're dealing with a -4. That means that this silicon has to equal +4. And again, we have to know that so that we can fix it on the right side. Because if we don't know silicon's charge, we can't write the right formula. So what that means is we need to balance this charge right here. Silicon we just figured out is +4. Chlorine is -1. So that means we're going to need 4 chlorines. Calcium is +2. Oxygen is -2, so we're good. And then all we really have to do is go back and balance some things. So we're going to need 2 calcium chlorides and 2 calcium oxides. Last one, I'll pause again, give you a little bit of time, and then when you come back, just check it and make sure that you're actually okay with the double replacement. Alright, so you're back, and this is what your answer should be for the final one of double replacement. So hopefully, again, practice these, make sure you're able to do them, because soon you're going to be putting these all together. So if you can't do them individually, there's no way you're going to be able to do them when they're all stuck together.